that would be wonderful. Okay, welcome everyone. Jethro is going to be talking about Schellekens Leech lattice and the very strange formula.
Okay, yeah, great. Firstly, thank you so much to the organizers for the invitation to speak here. It's a real pleasure. The context here is that I'm going to talk about holomorphic vertex algebras. So I'll say what that is in a moment. So let V be a vertex algebra, positively graded, V0 plus V1, etc., like this. And well, before beginning, we're going to assume a number of technical niceness conditions, which are probably familiar to most people. So rational here, say in a few words, means more or less like semi-simple Lie algebra. So it's complete reducibility of modules over the vertex algebra. C2 cofiniteness is a technical finiteness condition. Simple means no non-trivial ideals. CFT type means that so this V0 space always contains the vacuum vector, which is like the unit. The CFT type means it doesn't contain anything else. And we also assume self-dual. And so within this context, holomorphic means that the vertex algebra has only a single irreducible module, namely itself. So there are some well-known examples. If you take any even self-dual lattice, then the corresponding lattice vertex algebra will be holomorphic. And there are more exotic examples, like the very famous moonshine module, for example. So just before getting started, some straightforward consequences of these conditions. So we have this translation operator T, which by definition annihilates the vacuum vector. So CFT type implies that T V0 is going to be 0, which in turn implies that the weight 1 space, V1, is going to be a Lie algebra. And here the bracket is given by the 0 product coming from the vertex algebra. Self-duality implies the existence of an invariant bilinear form on the vertex algebra. And if you restrict this to the weight 1 piece, this just corresponds to the 1 product in the vertex algebra. So this goes back to work of Lie in the 1990s. And if we assume simplicity, well, then we get non-degeneracy of this bilinear form, and so this Lie algebra is going to be reductive by Cartan's criteria. Okay, so now it's, well, we'll see in a moment connections with modularity. So it turns out that holomorphic vertex algebras can only exist if the so-called central charge is a multiple of 8. And the particular case that we're going to work with today is central charge 24. And so there's this interesting dichotomy, which goes back to Schellekens in the physics literature and was made into a theorem of vertex algebras by Dong and Mason, which says that in this case of C equals 24, V holomorphic, like on the previous slide, this Lie algebra is either going to be abelian or semi-simple, nothing in between. And in fact, this follows from an even more interesting fact. So let me take this reductive Lie algebra V1 and decompose it into a direct sum of simple and abelian components. So now this bilinear form that I mentioned, I can restrict it to each component. And if the component is simple, then I'll say that it's K times the standard normalized bilinear form on that simple component. So C2 cofiniteness implies that these levels, K, actually have to be positive integers. And the abelian components don't really matter because the statement is going to be that for every component, both abelian and simple, the following equation has to hold. So and the equation is that this HI check, which is the Joule-Coxeter number of the component, divided by the level, has to be equal to the dimension of the whole Lie algebra divided by 24 minus 1. And here, just to unify cases, I write Joule-Coxeter number of an abelian component to be 0. So yeah, so where does this come from? So it comes from a well-known and deep relationship between vertex algebra, rational vertex algebras, rational C2 cofinite vertex algebras, and modular forms. So to say a few words about this, let tau be a parameter in the upper half complex plane, which I denote by h here, and set q to be e to the 2 pi I tau. So now we can write down the character of the vertex algebra, which is basically the generating function for the dimensions of the graded pieces. So we have the sum here, dimension. Oh yeah, can people see my cursor? Maybe I can use the cursor to point. You can see it?
Yes, yes, we can see it.
Okay, oh, I might use that, I might take advantage of that in the future. So we write down this generating function, and we have to do a peculiar normalization here, which has to do with modular forms. And it was proved by Zhu in 1996 that this is a general statement for C2 cofinite rational vertex algebras, that this generating function is going to be a modular function. In this particular case, because of the additional constraints, namely being holomorphic and C equals 24, this character has to be the following. Basically, the modular J function plus a constant. It's q to the minus 1 plus whatever the dimension of V1 is plus, and then all the further coefficients are determined. Okay, so what I also want to mention is a refinement of this story due to Miyamoto in 2000, where he introduces an element Z in a Cartan subalgebra V1 and replaces the dimensions of the graded pieces by traces of the exponential. And this thing is also modular. It's actually a Jacobi form. The full Jacobi transformation was proved by Crowell and Mason a few years later. But basically that means that it satisfies the equation that you see here at the bottom of the page. When you do a modular transformation on the variables, you pick up this exponential factor. I think most people will know what a modular form is, but let me recall some notation here. So a modular form, so I've been talking about modular functions, but a modular form in general of weight k is a holomorphic function on H, which satisfies this transformation property with respect to elements in the modular group SL2Z. And we also demand holomorphic at infinity, or rather at q equals 0. And the space of such things we call MK. And the main examples of these, of course, are Eisenstein series, and these generate, in fact, the ring of modular forms in SL2Z. So note that this function here is not modular in that sense. It's not holomorphic at infinity. It has a pole there. But anyway, so what are we going to do? So we want to exploit the great deal of rigidity that the ring of modular forms has. So we take this character, this Miyamoto character, and what we're going to do is first multiply it by exponential of some very particular factor multiplied by E2. E2 is the quasi-modular form of weight 2. So it's the same definition as on the previous page, but it's not modular, it's quasi-modular. And multiplying by this factor, this idea goes back to Schellekens, to my knowledge, or at least it was used by Schellekens. Perhaps he got it from somewhere else. And what this does is it kills this exponential factor that appears in the modular transformation of the two-variable character, and it turns it into a plain modular function. More precisely, if you take the Taylor series expansion of this product, then these coefficients pk will themselves be modular forms. Modular forms, except that because, as I said, they may not be holomorphic at q equals 0 form, which is a modular form of weight 12 that begins its expansion with q, and then the q kills the q inverse in the other character. And so now really pkq will be a modular form of weight now k plus 12. And the idea is to look at the coefficient of z squared, in other words, p2. Yeah, and let me record here the dimensions of the spaces of modular forms of various weight. So in 4 and 6, we have single Eisenstein series that generate space of modular forms. And it goes that way up to weight 12, where we acquire this extra cusp form. And then a curiosity is that in weight 24, the dimension goes back to 1. And then after that, it goes back to 2 again. So in weight 14, so what this means for this coefficient P2 is the following. So if I write out P2 as a Q-series expansion, I know that it has to be proportional to the unique modular form in that weight, right? Which begins 1 minus 24Q. So this gives me an equation between the first 2 coefficients in this series. Okay, so what do we have here? We have the dimension of V1, we have this non-degenerate bilinear form, which is level times the standard form. And we see also this trace here, which is basically going to be the killing form. It is the killing form. So the trace term here is the killing form, which is by definition, this is the definition of the Joule-Coxeter number, that this guy is 2 times h check times the standard form. So when you reorganize that equation, you get exactly this equation star. Okay. So, I think this equation is very fascinating. In particular, it implies a much stronger result than what I had attributed to these guys on the previous slide. What they actually proved is that this Lie algebra V1 is either 0 or it's abelian of dimension 24, in which case we can actually say more. The vertex algebra has to be the lattice vertex algebra associated with the Leech lattice. There is no other option. Or it's semi-simple and then its dimension is strictly greater than 24. And so most of this is immediate from that formula. Either the Lie algebra is 0, or if it has any abelian component, then the equation tells you that the dimension of the whole algebra is 24. But it also tells you in turn that the Joule-Coxeter numbers of all components are 0. So it has to be abelian. The fact about it being isomorphic to the Leech lattice is non-trivial. This is another result of Dong and Mason in a different paper at around the same time. The idea is that if the rank is 24, then you can show that the algebra has to be a lattice vertex algebra. And then out of those in rank 24, the Leech lattice is the only option. The Leech lattice, by the way, is the most interesting self-dual lattice of rank 24. It's characterized by the property that it has no roots. In other words, it has no vectors of norm 2, squared norm 2. And finally, if the Lie algebra is semi-simple, then take one of the simple components, then it has some non-zero Joule-Coxeter number, and that immediately implies that the dimension has to be greater than 24. In fact, something rather cool is that this equation, if we now start looking for what possible semi-simple Lie algebras we could have, this equation has exactly 221 solutions. It's not hard to see that it has finitely many solutions because if you imagine increasing the dimension, then you kind of have to start increasing the Joule-Coxeter numbers of the components. But you see that the dimension of a simple Lie algebra grows more or less like the square of the Joule-Coxeter numbers. You find that the total dimension starts growing very quickly. And you find if the dimension is too big, then you can't satisfy the equation. So you establish some rough bound on the dimension and then do a computer search, and you find that there are these 221 solutions. But not all of them correspond to holomorphic vertex algebras. Some of them you can rule out very easily. Others are very difficult to rule out. So the idea, and this goes back to Schellekens, and he found these 69 kind of actual solutions, or solutions to further modular constraints, that come by looking at the V1 module structure of other graded components of the vertex algebra. Right? So V2 is a module over V1, and so is V3, etc. And in any given case, there's only a finite number of modules that can appear. So what you can do, and then you can look at the spacer modular forms of weight 16 or 18 or 20, etc. And you get some huge system of, some huge integer programming problem, basically, which you're looking for non-negative integer solutions. And in that way, you can find that there's only 69 solutions. And I listed V2 to V7 here. I can confirm that you really do have to go up to V7 to get all the equations you need to kill off all the spurious cases. So it really is a lot of work. So what I want to describe in this talk is a completely different way to get from that 221 down to 69. And it essentially uses the Leech lattice and some vertex algebra theory. Okay. So to begin the story, I'm going to talk about what's called Orbifold Theory. So we take G, a finite order automorphism of our holomorphic vertex algebra. And we'll assume that everything is as before, there's C equals 24 and so forth. So firstly, you can take the fixed point subalgebra. This is a subvertex algebra of V. Now, every eigenspace of this automorphism on V will in fact be a module over this fixed point subalgebra. They'll all be irreducible. So that way we get n irreducible VG modules already, right? So we've got some irreducible modules for this subalgebra. And in vertex algebra theory, there's this notion of twisted module, twisted by an automorphism, which I won't really define. Indeed, I haven't defined vertex algebra. But it's this characteristic vertex algebra theory type construction where you have the notion of a V module but twisted by an automorphism. In particular, any G-twisted V module is an ordinary module in the usual sense, but over the fixed point subalgebra with respect to G. So to get more VG modules, you want to start looking at twisted V modules as well. So it turns out that there's a unique G-twisted V module. This is due to Dongley and Mason, and again comes from modular invariance type arguments. And the only thing I really want to say about this is that, so this module, so V itself was Z plus graded, non-negative integers. And the modules will also have natural gradings. So this VG in particular has a natural grading. And it turns out that its grading is of the form R over n squared plus positive integers over n. So what I'm describing here is the L0 grading, or the conformal weight grading, but I won't actually explain what that is. In general, I should have said irreducible module here, but would it? Oh no, it doesn't matter. Anyway, modules typically have this structure where they have a grading that begins with some particular special degree, eta, and continues in regular steps up from there. And so these numbers, this number eta, I'm going to call the rho of m, is known as the conformal weight of the module. And it's a rather important invariant of the module. That's the only thing I really want to say. It's a rational number. So we have VG, the G twisted module. We of course also have the G squared twisted module, which is also unique, G cubed, etc. So in this way we get n different twistings. And in fact, each of them splits into n eigenspaces of G. So in this way we get n squared irreducible modules over the fixed point algebra VG here. Okay. And now the category of modules over a rational vertex algebra is very, very rich, carries a lot of rich structures, a tensor product known as the fusion product, and indeed ultimately is what's called a modular tensor category under favorable circumstances. So in this case, so all I want to talk about here is this kind of decategorification of the module category, to use a fancy word. So what we proved, this is a number of years ago now, but we can parameterize these n squared modules in a nice way, a way in which you kind of summarizes all this data about the tensor products and these conformal weights. So, and this follows from these results of Dongli and Mason, and also the Verlinde formula, which is a theorem due to Huang. So this theorem says that there exists a parameterization of the modules, which I'm going to call W alpha, where alpha runs over an abelian group. The abelian group D is a discriminant form of a lattice. Okay, so what is that? So I take the lattice Z squared, Z plus Z, and equip it with a bilinear form whose gram matrix is that matrix written there, minus 2r n 0. Okay, so this lattice, I can look at its dual inside R2, if you wish. And then the dual divided by, contains the lattice itself because it's integral. The dual quotient is an abelian group of order n squared. And it comes equipped with kind of the shadow of this bilinear form. So I can talk about the norm, or the half norm squared of an element, which I write as alpha squared over 2. And so we can parameterize the modules in such a way that the fusion product corresponds to addition in this group, and the conformal weight of each irreducible module is given by this quadratic form. So you see, basically all of this structure is controlled by this single number R, which appears in the gram matrix. Remember, R can be read off from the grading of the twisted module. So this thing R is define modulo n, basically. Well, yeah, the invariant that I want to define is R modulo n. And we call this the type of the automorphism. And so the theorem is saying that the type then determines the structure of this fusion algebra, as it were. So for example, if the order of the automorphism is 2, then there are two possibilities. That as an abelian group, this group D is Z2 times Z2. So I write that as a table in the obvious way. And now if I label each element with its conformal weight, then the two possible options are 0, 0, a quarter, and 3/4, or 0, 0, 0, and a half in type 0. And the case we want to focus on, both for involutions but also in general for an arbitrary order, finite order n, is type 0. So what I write here is that if G is of type 0 and an additional condition, then we can do what's called an Orbifold construction. So this additional condition is that the conformal weights of all the modules other than VG itself are positive. This is very important. It has to do with subtle issues in the tensor category. Actually, I'm going to say that on the next slide. So with this additional technical condition, we can do the so-called Orbifold construction, which is the following idea. So it's to build a new holomorphic vertex algebra from a suitable collection of these VG modules. So if we assume type 0, then we have that the group D is Zn times Zn. Then what can we do? So I'll draw this table as I had before. So each column of the table corresponds to a twisted V module. As you see, I have this yellow column corresponds to V itself, which is obviously all the conformal weights of the components are 0, mod 1, because V itself is integer graded. The other column has both integer and half integer pieces. The Overflow construction consists of flipping a perspective and taking the first column, which again is integer graded, and taking the direct sum of all of those components and calling that a new vertex algebra, or rather proving that it has the structure of a new vertex algebra. Here the vertex algebra product in kind of this copy of Zn, right, that parameterizes these components. And so the I component and the J component, if I take their fusion product, I go to the I plus J components, so there's some intertwining operator there, and then by stitching together all these intertwining operators and checking some cohomological condition, we show the result is a vertex algebra. And it should be holomorphic. Yeah, and so when I say suitable subset, what I really mean is a maximal isotropic subgroup in this discriminant form D. And as I mentioned, we need this additional technical condition, and it has to do with some work of Dong, Zhao, and Xu computing quantum dimensions of irreducible modules. And we want the quantum dimensions to be positive, which ensures some conditions to do with braiding and Frobenius-Schur indicator work out correctly. But anyway, so we've got a construction of, you start with a holomorphic vertex algebra, some suitable automorphism, and use it to produce a new vertex algebra, holomorphic vertex algebra. And the idea is then you want to construct holomorphic vertex algebras by iterating this process, and hopefully you can produce more and more vertex algebras this way. Just while I'm here, let me observe that on the orbifold, so it comes with a Zn grading already, right? So what you can do is on the kth piece, so choose some root of unity and use that to label the pieces. And on the kth piece, I'll take the kth power of whatever root of unity I chose and define an automorphism that way. So now I get an order n automorphism on the orbifold. And now the orbifold of the orbifold is just the original vertex algebra. So you can always reverse any orbifold. I should say the cyclic orbifold, but what I'm developing here is what's called cyclic orbifold theory. Of course, there's a much more complicated, less well understood theory of orbifolds by non-cyclic groups. But yeah, so in this context, we have this reverse orbifold. So now I'll switch gears a little bit. So we want to, right, so we've got this way of stepping from one holomorphic vertex algebra to another, and we have this important invariant of the vertex algebra, which is this weight one space, V1. So I'd like to be able to say something about what happens to V1 when you do the orbifold, right? I didn't say this, but it was on the slide. The name we give to the orbifold is V orb G. I think it's clear that means the orbifold with respect to G of V. So to state this theorem, which is due to colleagues of mine, Sven Müller and Niels Scheithauer, so we introduce some rational numbers. So here we're n as a fixed numbers, the order of the orbifold we're considering. Now for every divisor of n, we have a number Cn of d. And these are defined by a system of linear equations, which are as written. For every divisor of n t, we have an equation. And this is non-degenerate, and it defines uniquely the set of numbers. Okay, so the theorem is that then the weight one Lie algebra of the orbifold of a holomorphic vertex algebra of central charge 24 satisfies the following bound, which is that its dimension is less than or equal to 24 plus linear combination of these coefficients, these funny rational coefficients, times dimensions of certain fixed point subalgebras in the original Lie algebra. So you see on this side, V1 is just a Lie algebra. And here I'm taking some fixed points by certain powers of this automorphism, the restriction of the automorphisms of V1, take their dimensions, combine them, and we can bound the dimension on the orbifold, which is useful because it's hard to get grips on the orbifold directly in some sense. Let me remark, I was involved in proving a special case of this theorem for certain values of n. This is in an earlier paper, which is now published. It was a very different argument. So in that case, we were able to prove it for those values of n for which the modular curve h divided by this congruent subgroup gamma 0 of n is genus 0, and then using particular properties of that, we're able to derive the formula. But now Sven and Niels have a completely general proof of the same result for general n. So let me maybe spend 10 seconds trying to say what the idea is. So it uses modular forms. The idea is that these the characters of the n squared irreducible modules that we have form a vector valued modular form for SL2Z. It forms a representation, it transforms according to the Weil representation of this lattice that appeared in the previous theorem. Okay, so what they do is they pick a very specific modular form of weight 2 on this congruent subgroup, which is as written, and lift it to the joule Weil representation, so the joule of the representation by which the characters transform. And the coefficients here are kind of chosen to get the result that we want, in a sense. But of course, there's also huge numbers of constraints, so you can't really just choose anything you like. It's highly constrained of what you can do here. But if you choose this particular modular form, then pair the two together, the result is then a modular form on SL2Z of weight 2. So that's just the same thing as a 1 form on the Riemann sphere. So you can apply the residue theorem and you get an equation. A certain coefficient in this guy vanishes. And that equation is just, again, there's more work here, but it's this equation here. Actually, I lied slightly in the abstract. I said they use the Deligne bound on the growth of coefficients of a weight 2 cusp form to get this result. In the same paper, where they prove this theorem, they go a lot further. They use the Deligne form, because you don't have to pair with this particular modular form. You can pair with other modular forms of weight 2. And if you have a cusp form, so if in particular, if n is a prime such that the genus of that modular curve is non-zero, then you have these weight 2 cusp forms that you can apply this machinery to, and then you get interesting, stronger constraints on the dimension. So you don't actually need the Deligne bound for what I'm describing here. But anyway. Now let me switch gears again. So now we're talking about Lie algebras. Let G be a simple Lie algebra. Let's introduce the usual constructions, a cation, roots, positive roots, identify the cation with its joule. We have the Weil vector, the sum of the positive roots over 2. And now there's a theory due to Victor Katz about classification and such of automorphisms of simple Lie algebras. I've said simple, but all of this can be adapted to the semi-simple case. So let G be an inner automorphism of order n. So one can conjugate that automorphism to one of the form exponential of adjoint of some element in the cation, or called delta. And one can do this in such a way that the following so-called very strange formula holds, which says that, so now if I take the eigenspaces of the automorphism, call them G sub k, so they're all going to be roots of unity, obviously, the eigenvalues, and take a particular linear combination of those dimensions that you see on this side, the dimension of G over 24 minus this guy, can be expressed rather simply in terms of the norm, the distance, basically, between delta and this kind of special vector, Weil vector over H check. Now, like until now, we've seen the 24 appearing. That's because we're working with central charge 24. This 24 kind of is strange. That's why it's called the strange formula. I mean, the original formula was the Freudenthal-de Vries strange formula, which writes the norm of the Weil vector in terms of the dimension over 24. And this formula is a very strange formula, not because it's stranger than the strange formula, but because it generalizes the strange formula. When the automorphism is the identity, we get back the strange formula. Anyway, I want to connect this to this dimension formula from the previous slide. So firstly, you do a little bit of manipulation here, massaging. So let's assume that this automorphism is what's called quasi-rational. So if I have an automorphism of a rational vector space and then complexify everything, then the dimensions of GK1 and GK2, with these eigenspaces like we see here, if the GCD of n with K1 and with K2 are the same, then the dimensions are going to be the same. It's a sort of Galois symmetry, right? It can't, since it comes from the rationals, it can't depend on any Galois symmetry of C. So you call an automorphism quasi-rational if it satisfies that condition. Okay, so if the automorphism is quasi-rational, then we can rewrite this left-hand side of the very strange formula in this more compact form. So 1 over 24 times the sum of bt over t. Bt are some integers which are exponents that appear in the characteristic polynomial of the automorphism. Okay, so whatever. So you can rewrite it in this way. This is an elementary calculation. And now, so now we come to the theorem. So let V be, as I've been describing until now, a holomorphic vertex algebra, so forth. And let's assume V1 is a semi-simple Lie algebra. And let's take delta in V1 and exponentiate it and consider this automorphism G, which is exponential of delta. So let me assume that it's quasi-rational. And let me also assume that it's type 0 and positive so that I can apply the Orbifold construction. So then we get the following formula, the following alternate version of the bound on the dimension. It says that the dimension of V1 orb is no greater than 24 plus some now of these sort of norms of distance between delta and rho I over hi, but these are for each of the components of the Lie algebra. So the proof, I see a bit of Portuguese leaked into the talk. So the idea of the proof is, so firstly, one can show, so these dimensions of fixed point subalgebras you can rewrite in terms of these exponents that appear in the characteristic polynomial. It's another elementary calculation. We substitute this into the dimension formula. You see these dimensions appear here. Simplify, combine this property of these BTs with the characterization of these coefficients C, N, D that appeared. Simplify a bit. We end up basically with this expression here, 1 over 24 sum of these BTs over T. So we now apply the very strange formula and we get the result. Okay, so although it's elementary, it's a combination of complicated facts in a very elementary way. So clearly, the most interesting thing to do at this point is to let delta be the following thing, right? You want to make the right-hand side 0. So let's take the exponential of this specific vector. On each component, it's given by rho 1, rho I over hi, check. So then the right-hand side here obviously vanishes, or rather is equal to 24, plus something that vanishes. So we find the dimension of the V1 of the orbifold is less than or equal to 24, but that we know that that implies that it's either 0 or 24. It can't be 0 because V1 orb already contains, say, delta itself. It contains a Cartan subalgebra already. So the orbifold V1 has dimension 24. Furthermore, it must actually be the Leech lattice vertex algebra, which means in turn that our original V must actually be an orbifold of the Leech lattice vertex algebra. It's the inverse orbifold. So we kind of start with an essentially arbitrary or hypothetical holomorphic vertex algebra with semi-simple V1 piece. And you find that it has to be a orbifold of the Leech lattice, which is quite striking, I think. Okay, so that's the main theorem. There's a few things I need to tie up at this point. Firstly, obviously we need to check some things. Why does this automorphism actually satisfy the conditions of the theorem? In particular, why is G quasi-rational? Well, that's an exercise in Victor Katz's book. Why is G positive? This is a little more difficult, but it has to do with, well, you decompose V as a finite direct sum of integrable modules over corresponding affine Lie algebra, and look at the sets of weights that appear in these modules. And this, of course, is very well understood, and you really can get a handle on this. And then you want to see what happens when you do twists. But again, you can sort of it's hard to describe, but you can show that none of the twisted modules develops a negative conformal weight, so the automorphism is positive. The most interesting part, I think, is why G is type 0, because a priori there doesn't seem to be any reason why this should be true. And quite cool thing is that this original equation, right from the back at the beginning of the talk, this formula star, is exactly what you need to guarantee that this automorphism is type 0 and therefore is suitable to be used as an orbifold. Which it began life in a way that had nothing to do with orbifolds somehow. So this is quite interesting. And this fourth point is a subsidiary to the third point. It actually follows from the same kind of yoga. So I want to, maybe I'm running a little low on time, so I'll go quickly through the next slide. Oh, it's not so bad. Anyway, the point is, so there's an inner automorphism defined as a exponential of an element of the weight 1 space. So such automorphisms of vertex algebras are very, very well understood. In particular, the twisted modules can be very explicitly constructed. This goes back again to Lie a long time ago. So this VG in particular can be identified with V itself, and you can describe the grading explicitly as a kind of shift of the grading on the vertex algebra itself. So checking that this automorphism is type 0 boils down to showing that this shift vector that appears, or rather this number, 1/2 delta delta, lies in 1 over n, right? So a priori it could be in a rational number that lies in z over n squared. You want to show that actually lies in z over n. And so how do we do this? So we write it out explicitly, we get the sum of norms, write each norm in terms of the normalized norm, as it were, invoking the level. Now use the strange formula to write these norms of Weil vectors in terms of the dimension of the components. Now we see we've got a k over h check in this equation, so we'll use formula star as promised. And now this sum has got the same denominator in every term, and the numerator is just the dimensions of the components. So when you sum them all together, you get dim v1. Now we're going to use the formula star again to rewrite this as k over h for any given one of the components. And basically that's it, because the order of the automorphism is just the lowest common multiple, more or less, lowest common multiple of these HIs. And we've shown that this number is in a multiple of whatever that is, so it works. So, but what's more interesting, I think, is, so we've shown that we've started with some kind of hypothetical unknown holomorphic vertex algebra. We've shown that it has to be an orbifold of the Leech lattice, but we know the automorphism group of the Leech lattice vertex algebra. So kind of this, we've got a lot of control now over how you construct V, right? So the automorphism group of the Leech lattice itself is this, of course, almost sporadic group. It's like 2 times the sporadic group. Conway group, Conway 0, which has that many elements, consists of 167 conjugacy classes. And of course, the isomorphism type of the orbifold depends on the conjugacy class of the automorphism. And the automorphism group of the vertex algebra is now an extension of this group, Conway group, by a torus. And the torus is just the quotient of C24 divided by the Leech lattice. So this is known again. This probably also goes back to Dong and Mason in their work on automorphism groups of lattice vertex algebras. So what do we do? So we know that we get back V by orbifolding Leech lattice vertex algebra by one of these automorphisms. So what we're searching for then, remember that the goal was to get that number 221 down to 69. So we search for pairs that consist of an automorphism of the Leech lattice vertex algebra and a semi-simple Lie algebra on that list of 221. So I've written the automorphism in the form T sigma. T is an element in the torus and sigma is an element in the Conway group. And this pair has to satisfy whatever compatibility conditions come from the fact that one automorphism is the reverse automorphism of the other one, right? By the other one, I mean GG, right? Which means what? If you recall, GG is exponential of this guy delta, right? So any semi-simple Lie algebra has this kind of canonical automorphism, GG. GG has to be the reverse of this thing coming from the Leech lattice. And so you can read off some simple consequences of this compatibility. So the order of sigma has to divide the order of T sigma, which has to equal the order of GG. So I'll call that number n. And now if you go back to the dimension formula, which you now know is not just an inequality, but an equality, because you have equality to 24, and kind of unwind what it's telling you, then you get this equation. I realize I haven't defined rho sigma. Rho sigma is some quantity that you can read off from sigma by, again, from the exponents in its characteristic polynomial. So it's something you can read off by, you produce your list of 167 conjugacy classes of automorphisms. Each one of them, you can compute this number, rho sigma. And you find that 24n times 1 minus rho sigma is equal dimension of your Lie algebra, G minus 24. And the ranks on the two sides have to agree. And maybe to deal with a slight annoying issue, I'll state this fourth condition, which is of course also has to be satisfied, but it's that this T sigma has to be type 0 in particular it's the reverse of a type 0 automorphism, so it's also type 0. This in itself imposes a condition on T and sigma, that it be type 0. And okay, so you put in the computer, you've got a list of 167 automorph guys and a list of 220 on the other side, and you see which pairs can possibly be pairs that satisfy these conditions. Find only 69 work, which are of course 69 determined by Schellekens and painstakingly constructed one by one over the years since then. So that's it.
Thank you so much, Jethro. Let's clap for the speaker.
Thank you.
Yeah. So feel free to unmute yourself and go for any questions you may have. And maybe I'll start. So Jethro, do you have a less painful construction of each of this like in mind?
There's a lot more to be said. I mean, me personally, no. I mean, you could, what I should say is Sven and Niels define you can say all of these vertex algebras are obtained as orbifolds of the Leech lattice vertex algebra by specific automorphisms. This is what this result says. So Sven and Niels also define something that they call a generalized deep hole in the Leech lattice vertex algebra. So what that means, so this goes back to study of the Leech lattice. There's something called a deep hole. So what a hole in a lattice, firstly, is a point that's kind of maximally distant from points of the lattice. So you think you're in the ambient space of this lattice, and if you're off the lattice, then you can kind of try to go to a point that's maximally distant from the lattice, and that's called a hole. Now in the Leech lattice, holes come in, well, in any lattice, holes come in different conjugacy classes under the automorphism group. And in the Leech lattice, a deep hole is kind of So a hole is a local maximum for the distance. A global maximum is called a deep hole, right? So it turns out that under the action of the automorphism group, there are 23 conjugacy classes of, or equivalence classes of deep holes. Each of these can then be interpreted as an automorphism of the Leech lattice vertex algebra. And if you do the if you do the orbifold by the automorphism corresponding to a deep hole, you get one of the other Niemeyer lattice lattice vertex algebras. So this was already understood in lattice theory, like without reference to vertex algebras. You don't have to understand vertex algebras to know this fact. So it was understood that the 23 Niemeyer lattices corresponded in a natural way to the 23 equivalence classes of deep holes. But after this reinterpretation of the deep hole as a certain kind of automorphism of the Leech lattice vertex algebra, Sven and Niels went ahead and well, you can almost characterize these automorphisms in terms of this dimension formula. So they're, in particular, the bound, the inequality that appears is saturated for such automorphisms. But there are other, and there's also a condition on ranks. But they're not the only automorphisms with that property. So they define a generalized deep hole to be any automorphism that saturates that bound in the dimension formula and satisfies a condition on rank of the fixed point subalgebra. So all of these automorphisms that occur, that can produce a holomorphic vertex algebra as orbifold, have to be generalized deep holes. So this follows from the definition. So what they have very recently proved is that these 69 other cases are in bijection with the generalized deep holes of the Leech lattice. I was talking to Sven this week, and I think they just proved this week, basically. Or they uploaded a new version of the paper where they've now proved this result, which I think they've known for a while, but now they've got it. Definitely. I don't know, yeah, so I don't know if this really answers the question, but I think it's, yeah, I take it as an advertisement for this notion that they've come up with, which I think is very interesting. It's kind of, you take something which came from lattice theory and you kind of reformulate in terms of automorphisms of vertex algebras. And now you can talk about deep hole, generalized deep hole of another vertex algebra. So it's kind of been freed of this origin to do with the Leech lattice specifically.
Thanks. Any other questions for Jethro? Okay, if there are no other questions, let's thank Jethro again. I hope to see you all next Thursday for Naoki's talk at 1 p.m. Mountain Time.
Mm-hmm.
Yeah, thank you, Jethro.
We'll be there. Yeah. All right. Yeah. Thank you so much.
Thank you. Bye-bye.
Oh, sorry. I'm still sharing.
Oh, that's cool.
Yeah.
Okay. Take care, everyone. Hope to see you next Thursday.
See you later.